Have you ever stopped to think about what it really takes to build one of those massive enterprise networks? The kind that just works? Well, I can tell you it's not magic. It's actually a really clear process, a life cycle, really. It's all about designing it right, managing it smart, and knowing how to fix it when things go wrong. So let's dive in and break that down. All right, to get us started, let me throw a question at you. What in the world does a huge, sprawling city have in common with your company's network? Well, it might sound a little strange, but the answer is they both need a really solid blueprint, right? A plan for how they're going to grow. They also need a way to manage all the traffic flowing through them. And of course, they absolutely need a plan for when emergencies strike. And those three things, that's the heart of the network lifecycle. We're talking design, manage, and fix. Okay, so let's tackle the first part, designing the blueprint. I mean, think about it. A city planner wouldn't just start throwing up buildings, right? They lay out the roads, the zones, the whole master plan before a single shovel hits the ground. It's the exact same idea for a network architect. You have to design that logical structure first. Just imagine the difference between, say, a tiny little village and a massive metropolis. You know, in the early days, networks were a lot like that village. We call them flat networks, where basically everything is connected to everything else. And for a small setup, that's fine. But it gets chaotic fast. If you want to scale up, if you want to build a real city, you need structure. And that's where the hierarchical model comes in. So this hierarchical model, it's really built on three main tiers or layers. Down at the bottom, you've got the access layer. Think of these as all the local streets and driveways. It's where all the users actually connect to the network. Then you move up to the distribution layer. These are like your major city arteries, collecting all that local traffic and, importantly, enforcing the rules of the road. And then at the very top, you have the core layer. This is the super fast, high-speed freeway, the backbone that connects all the different parts of your network city together at incredible speeds. So the big question is, how do you make this network city tough? How do you make it resilient? Well, it all starts with redundancy. You got to have backups for your critical gear. That way, one little outage doesn't take down an entire district, you know? We also do something called link aggregation, which is a fancy way of saying we bundle a bunch of physical cables together to create one giant, super fast digital highway. And maybe most important of all, we create what are called failure domains. This is a huge deal. It means if one neighborhood has a massive traffic jam, it stays in that neighborhood. It doesn't gridlock the entire city. All right, our blueprint is solid. The city is designed. What's next? Well, now we have to manage it. And here's the golden rule. You can't manage what you can't see. So the very first step is just getting visibility. It's kind of like a city taking a census to figure out exactly who and what is living within its borders. And how do we take that census on a network? We use something called discovery protocols. The easiest way to think about them is that they let devices automatically introduce themselves to their direct neighbors. It's like saying, hey, I'm a switch and you're a router connected to my port 5. Now, there are a couple of different languages they can speak, like Cisco's own CDP or the more universal open standard LLDP. But at the end of the day, the goal is the same, to automatically build a map of who's connected to who. You know, another piece of this visibility puzzle that people often forget about is time. It's absolutely critical that every single device on the network agrees on the exact same time. We make this happen with the Network Time Protocol, or NTP. It basically syncs up all the clocks to one central, trusted source. I mean, a city needs a universal time for everything to run smoothly, right? From train schedules to bank hours. The network is no different. So why is this such a big deal? Well, there's a great quote about this that really hits at home. When the time is not synchronized between devices, it is impossible to determine the order of events. Just think about that. It's like trying to solve a crime when every witness gives you a different time for what they saw. It would be total chaos. NTP makes sure that when something happens, all the logs tell one consistent chronological story. Okay, so we know who's on our network. That's a great start. But knowing what they're doing and, more importantly, how the infrastructure itself is holding up, that's a whole other level. This is where active monitoring comes in. It's basically the network's version of a city's traffic cameras, its power grid sensors, its emergency alert systems, all rolled into one. And one of the classic tools for this job is SNMP, the Simple Network Management Protocol. The way it works is pretty cool. You have an SNMP manager, which you can think of as the city's central command center. Then, on every important device, every router, every switch, you have an agent. That agent is like a little sensor, just waiting to report back. And the list of all the things it can report on is called the MIB. So the command center is constantly pulling or asking these agents for updates, giving it a real-time pulse on the entire city's health. And this isn't just a one-way street, it's not just passive listening. That command center can actively get specific information like, hey, how busy is that router right now? It can even set a configuration to make a change from afar. But what's really powerful is that the devices themselves can send out their own emergency alerts. We call them traps. So when something critical happens, like a major link goes down or city's bridge suddenly collapsing, it sends an immediate trap straight to the manager. Now, SNMP is fantastic for checking stats and getting alerts. But for everything else, we have syslog. You can think of syslog as the network's universal diary or messaging system. It's a standard way for pretty much any device to send event notifications, we just call them log messages, to a central logging server. And this thing captures everything. From, hey, a user just logged in, to, oh my god, the entire system is on fire. The real magic of syslog, though, is how it organizes all this information. Every single message gets a severity level tag on a scale from 0 to 7. Level 0 is an emergency. That's as bad as it gets. The system is unusable. All the way down to level 7, which is just a debugging message, something an engineer might look at later. This system is basically a giant filter. It lets you instantly slice through all the routine noise and focus on the real 5-alarm fires that need your attention right now. So, let's recap. We've designed our city, we're monitoring it around the clock. But let's be real, no matter how perfectly you plan, things are going to break. It's just a fact of life. And that brings us to the final, critical phase of the life cycle, troubleshooting. This is your network's emergency response team, the firefighters, the paramedics, the whole shebang. And what's the #1 rule when that emergency call comes in? Simple. Panic is not a strategy. Process is. A real pro doesn't just start randomly trying stuff. No way. It's all about following a calm, methodical, logical process to hunt down the root cause of the problem. And where does that process always begin? With good documentation. I mean, you can't fix what you don't understand, right? Having accurate network diagrams, device records, performance baselines, that's the map your first responders absolutely need. Without it, they're just flying blind in the middle of a crisis. One of the most tried and true methods is what we call the bottom-up approach. It's exactly what it sounds like. You start at the absolute bottom, the physical layer. Literally, is the cable plugged in? Is the light green? If that's all good, you move up a layer to data link. Are the switches talking into each other correctly? Still no fix? Okay, up again, to the network layer. Are the IP addresses right? Is routing working? By methodically climbing up this stack, you make sure you don't spend 3 hours troubleshooting some complex software bug when, oops, the problem was just a cable that got kicked out. Okay, let's pull all these pieces back together, because it's really important to see that this isn't just a straight line from start to finish. It's a continuous repeating cycle. So if there's one thing to take away from all this, it's this. You have to design for scale and for things to fail. You have to manage with constant, real-time visibility. And you have to troubleshoot with a repeatable process, not with panic. And the beautiful part is that each of these phases feeds back into the others. What you learn from troubleshooting informs your next design change. And that creates a network that isn't just fast, but one you can actually depend on. And that is why this whole cycle is so incredibly important. There's a quote that ties it all together perfectly. A well-designed network limits the size of failure domains. What does that really mean? It means the smart decisions you make way back in the design phase, they directly impact how bad things get when an emergency eventually happens. Good design makes for smaller fires to put out later. So that leaves us with one final thought to chew on. As our networks get smarter and more automated, who's going to be that first responder in the future? Will it still be a person jumping on a keyboard at 3 a.m.? Or will it be an AI that spots and fixes the problem before any human even knows something was wrong? Now that is something to think about.